Hello, my name is Angel. We have Brian and Efron, and we're bringing you the exhaust-driven turbine. This was our initial introduction idea. It was to put a helical fan or turbine right now in an exhaust pipe in order to generate electrical energy. We first started off with thinking about cars, especially hybrid cars, in order to generate electricity so they can be used. So how it works. Our initial concept was to have a helical turbine design where the airflow would make it spin and then generate electricity. How that's going to work, we're going to see later on in the presentation. We moved on from this design because the issue was these bars right here. We would require a lot more building, and since it's a small cylinder, it would need a lot more, you can't get your hands in there in order to fabricate. So we completely changed the design in order to transmit power. Motivation. So the market now is going more into hybrid and hybrid cars since the introduction of the Prius back in 1999. So that market has increased over the past 15 years. So through our testing, we noticed that the pipe size for the cars wasn't really generating enough electricity or spinning the turbine to what we would think would generate a good amount of power. So we thought of going big, so making the pipe size bigger. So our main motivation was to reduce oil consumption. How we do that, the more hybrid cars there are, the less oil we're going to require. And then preservation of the environment, and what we're going to do is use the wasted energy and increase the overall efficiency of the car. So, global environmental impact. Right now, getting oil is really bad for the environment. You have product pollution, all these leaks, you have the transfer of oils, mentioned the BP oil spill, all that has an effect. Also environmental destruction. You don't see it here. Why? Because they go to other countries that don't have any regulations and affect the people, the environment as well. What happens when this environment is all used up, it's eventually going to have to come to here, to the United States, and then take over the world. So this is also little pictures of what I call conflict areas. So in Africa, where a lot of the oil companies are going, it's affecting their water supply, their environment, and there's a lot of military force on getting that oil in order for it to be cheaper for the manufacturers for here. So our global market, we started off in cars, and then we made our way up to trucks. The reason we'll further explain, but it has to do with the actual hole size for the pipe. Bigger the hole, the bigger the turbine we can make, the more it can generate electricity. Right here we have a fleet of trucks. These are called our arc mover trucks, and then we can even go as low as 5.0 liter trucks, things like that. All these, there is no advance in making them hybrid or any advance in making them more efficient. All these are paying a lot more than a consumption of car. All your goods and stores use trucks. Everything is moved through trucks. As far as fabrication, we use our 3D printer to do different types of testing for different blades. Now, our constraints as far as lab equipment, obviously the exhaust pipe is going to be at high temperatures, 200, 300, 400 degrees. To test that in a controlled environment is not really feasible as far as what we have here as availability. And also, just for future explanation for testing, we did all this in ambient temperature. So further research would have to be done with 200, 300 degrees, depending on where we're going to place it on the pipeline to get more accurate results. But usually, the hotter the air, the lower the density, which increases your velocity. So that we couldn't really test. Also, there's carbon dioxide coming out of the car. That's not really safe and conducive to be testing. Apparatus. We used the multi-speed fan here in order to try to reproduce the velocity flow that would come out of a car the best we can. So right here we have adjustable diameter sizes, and based on that we were able to formulate our own experiment, because we had to create our own way of experimenting on whether adding the turbine was going to create too much back pressure for the engine to even see if it's efficient. So that was our first task. And with this we were able to change, you go through 3 different diameters.
Is that like a Venturi type system?
Yes. So it's a system we have here in our transport lab with Dr. Tremonti, who let us use that many hours. So we first initially thought of a pipe like this, which is a conventional car, is about 35 millimeters. And these are bearings that we initially used. We'll go into that a little bit more because we actually use the helical design turbines. So for example, we put this here, ran the air through, which you will see later, we have videos, and then it would spin at a certain rate. Now these weren't all that successful, but we'll go into that. And then challenges. Obviously the main challenges was to maintain positive efficiency. So if adding a turbine really reduces the efficiency of the engine, then it's not really worth it. So that was one of our main things to try and figure out with experimenting. Also, the size limitation of the exhaust was a big challenge, and the key thing was getting something out of this. We didn't just want to have a turbine spinning and not doing anything. We wanted to generate electricity. And how we do that will be further explained.
Here are the first designs that we came up with, and our main objective for these was to focus on the area of reduction of flow. So the design on the left was the very first design we had, with an area reduction of about 20%. We figured the least area reduction we have, then the least amount of back pressure increase. So then we have the second design that has a little bit more of a reduction in area, but it still has the thin blades and it allows for the flow to go through. And we realized that the area reduction of the turbine is not necessarily what we need to focus on. Is the area reduction of the input pipe, which overall is smaller than the turbine itself. So we have the turbine with the bearings we purchased. We designed around the bearing so we can make sure a tight fit. And these are turbines A and B, which the first one is actually both turbines are a conical shape on the inside. So they start out the same diameter as the inside of the bearing, and the cross section increases as it goes along, and the blade also increases in the length. So you can see in the design on the left, the initial blade is almost flush, and towards the end it almost closes the entire diameter. And this, it did generate some movement, but not as much as we were expecting. So we've redesigned the turbine with a smaller cross section in the beginning. So the blades create a smaller initial free-flowing diameter in the middle. So here we have the turbine A on the left spinning. It does spin, but it's moving very slowly. So we decided that the blades are not, taking effect early enough. So then the turbine B, with the blades going more towards the center, we have a lot more movement. But still not really as fast as we were hoping for. So we figured this isn't working. We need to optimize our design. We need to come up with something new. So here are the back pressure differences. The blue line on the chart represents the pressure readings without any turbine on the pipe. The green line represents turbine B, which is the faster spinning turbine, and then turbine A is with the slower spinning. And we can see that there's a dramatic increase in the back pressure in the system. We have 110% increase with the first turbine and 53% increase with the second one. So obviously we can't have 50% increase in back pressure.
Also, just to add on, how we tested this back pressure, we drilled a hole into the pipe, and we used the pitot tube to measure the pressure in inches of water. And then that would be our blue line. That's our reference point. So there we can see what the effects are. And then after adding turbine A, we measured again, and then after adding turbine B, we measured again. So that shows the difference between what we initially started with what we ended up with. And also the bearings have to do a lot with it, the friction. So we use lubrication to get it, this particular bearing as easily movable as possible to be able to have the best effect. That's even this bearing completely did not get the effects we want.
So we see how we tested the turbine was to hold the pipe in front, and the turbine sits around the outside of the pipe. And we decided that it might be a little beneficial to have the turbine inside of a bearing so that we have less of a area spinning. In this case here, we have most of the weight of the bearing is along the outside diameter. So most of the weight is what has to be spun by the turbine. We want as little weight as possible adding to the turbine itself. So we found an ultralight or ultra thin bearing that would fit inside of the metal housing there. So this will be, the outer diameter is 3.5 inches in this case. So this will fit inside of a pipe, and the turbine would fit inside of this bearing. So we designed the turbine here as just an initial design to test the ultra thin bearing. We have the channels along the outside, which are intended for our magnets to be glued onto, and we made it just as light as possible to hope for as much speed as possible. So we put it in the bearing, printed it out, and once we hooked it up to the machine, you see it spun a lot faster than we were expecting. So we have a piece of tape on the end to show how fast it's spinning. We were hoping to count the revolutions we did before, and obviously it's spinning a lot faster than we were expecting. So we figured this is what we want to do. This is our path going forward. We want to use the ultra thin bearing with the larger turbine.
So based on the last results, as we saw in the video, we noticed that by just changing the bearing and putting a thin section bearing that actually provided a lot less friction compared to the other standard bearing that we were using, the design was reaching the speeds that we needed in order to generate some power. So we continued with the design to be able to increase the diameter of the size that could fit relatively close to the gut that has our apparatus. And this is the images of the final one of the final designs and lengths in the blades. We added about a 10 diameter gap in the middle so that there's not too much of a constraint, and we optimized that through some previous Solidworks simulations.
Also, we added channels. This was another added value to our idea. Instead of having a glue magnet, we could just use its own magnet system to hold it in place, and then just put a cap at the top. Right here, this is the actual capped turbine. In here, there are 6 rows of 4 magnets in each row, and they're all held in there by using their own magnet system.
And so from some initial SolidWorks simulations with the latest model that we had, we first wanted to determine whether there was some areas of zero velocity or turbulence parts where the flow is not flowing properly. And through our results showed that the air velocity was distributed evenly through the helical design that we decided to go with. And this would benefit in reducing the back pressure, as in compared to an axial blade, they would provide a lot of back pressure when hitting the initial propellers. So in this simulation, after measuring the amount of velocities, we decided to go with it and go into further experimental testing for receiving experimental data. And so another one of the biggest challenges that we mentioned earlier was the transfer of power. Originally, in the first model, you noticed we had a helical design that had a shaft centered in the middle, and the original idea was just to transfer the power transferred through gears, maybe connecting to an alternator. But then we came to the idea that if we were to actually create the turbine itself to be in a sense, acting as an electric motor. We can be able to attach copper wires around the cylinder and magnets so that as it rotates, it will be able to create magnetic induction in the wires. And so this is the principle that we followed. We did research on the standard ways of magnetic induction, which uses the coil and magnets. Typically, a magnet, when thrusted forward and back onto a coil, generates an electric current. But in this application, we decided to go a little different, moving it side to side, which still creates a current within the coil. As a magnet comes towards the coil, it creates one positive direction of the current, and as it moves away from it, it reverses the current. So naturally, we were actually creating, as the magnets were spinning, we were creating DC current. So another thing we needed to do if we wanted DC, we needed a bridge rectifier in order to bring that to a DC level that we can use to provide power of DC motors or electric components. So the coils themselves, since this was all custom, our apparatus had about 5 inches in length. They were custom fabricated because they didn't have any coils of that oval shape size. We decided to go 500 turns for each of the coils, since that would, we calculated it would cause, or give us about, voltages of, each coil would give us a voltage of about a battery, 1.5 to 2 to 3 volts, which was a good combination so that we can change the configuration of the coils to find the best power output. And so this is pretty much how we decided to transfer the power. As Andrew previously mentioned, there was segments in the final turbine like this right here that the magnets would be put into inside slots, and it will be easy for it to be sustained as it's rotating, to be able to be put next to coils in this manner and generate power. So another thing we had to make sure is to design a multi-fitting coupler that would not only encompass the bearing as well as the turbine, but also the casing for the magnet coils that we're going to put on. And we had to make sure tolerances were right in order for the bearing not to touch anything and not to lose any not to lose any energy as it's rotating properly. This is just one of the designs. And this is the current model we have with all the components put together. The coupler and the spacings, and the magnets will just be placed on top onto this clear tube. And clear tube is just for visual effects to see the rotation of the turbine. So this is the current assembly we had. We had the magnets placed inside the turbine in the slots, as well as the coils, which in reality are actually glued onto the clear tube, so they're pretty sustained. And also the key important part was we had to make sure the coils were evenly distributed in degrees as the degrees of the spokes of the magnets, in order for it to all generate power at the same time when all of them cross the areas of the coils. And this is one of the final examples we have of the spinning turbine generating power. One of the key differences we did in this experiment, as you notice, the tape is for visual effects to see it spinning, but we actually decided to go in a vertical direction instead of a horizontal, because we changed our shift, or we shifted our goal towards trying to focus on semi-trucks and larger trucks that actually have exhaust pipes pointing upward. And using that replicating effect, we were able to generate voltages and amplitude that we're able to measure and show in later charts.
We had to do a comparison between the flow we're getting from the multi-fan apparatus and between the flow we're going to actually get from different types of trucks. The table on the left shows multiple engine sizes ranging from standard pickup trucks to commercial trucks, fleet trucks, to even semi-trucks. We see the different flow rates depending on the engine speed. So even at idle for a 5-liter engine, we've got 31 liters per second of volume flow. Then looking at cruising speeds between 2,000 and 3,000, we have between 80 and 150 liters per second, even for just standard pickup trucks. We measure the velocity of the flow coming from the apparatus, and with the cross-sectional area, we're able to determine the flow, and we have between 60 and 70 liters per second. So we do have a realistic flow in our experiments, and so our results will be fairly accurate.
For the electrical part of the results, we were able to analyze first in order we need to determine in what configuration we had to connect coils. Since we had 6 coils of 500 turn each, we didn't know if we were to need to put in series or parallel, so we did a preliminary experiment measuring the amount of output that was producing from series and parallel combination. And we noticed that in the series combination, it was actually producing a lot more power, even compared to the parallel. And it wasn't evenly distributed of increase or decrease of voltages and amps. It was actually, series was actually helping receive a lot more efficiency. So we went with connecting the 6 coils in series. And through one of our maximum speeds that we were able to generate, as well as maintaining, putting strong magnets into the system, we were able to generate for the 6 coils about 500 megawatts milliwatts of energy in total compared to the voltage and the amps that it was providing. Initially, we probably were expecting a bit more of energy coming out from the system, but for the amount of back pressure that we soon calculated in between slides, we noticed that this actually was a very good positive outcome. Results, even though it's 0.5 watts, there was something that we actually can generate and be able to move some components or probably add a little more back to the system and electrical power.
So this is the back pressure results. This is proving that it works. So we did the same process. We had the feeder tube measuring the pressure at 9 amps, 10 amps, and 11. And then adding the turbine. This is the red curve. So right here at 9 amps, which is usually what cruising speed is, comparing to the trucks, it was at 0.19% difference in change. Here it was 3%, and then here was 0.12. So that's an average of 1.21% increase in pressure, which is pretty phenomenal. It's a great result. We're really happy with that. And this was our timeline for the project, and we are right here. Results and presentation currently. For cost analysis, our whole project, since we're using KLA Internet parts, came out to $955. We still have to do a cost analysis on actually manufacturing this out of aluminum, so it doesn't interfere with magnets, which we have to do future consultation and see how much it would cost to manufacture this part. Thank you.
All right.
Any questions?
Okay, you're 2.5 minutes over, so try and work on that. Okay, the system when attached to, the system that you're proposing when attached to an exhaust system assumes that that exhaust system will be from a normally aspirated type of operation, correct? Not a turbo.
Right, not turbo related at all.
So you may want to say that, because a lot of the vehicles out there nowadays have turbo assist. And this would not operate very well with that kind of system without causing some adverse operating impacts on the vehicle.
So this would be more ideal for non-turbo?
Non-aspirated, so you may want to make that very clear in your opening comments preferably. Okay. Go back to that slide with the turbine A and B. Let me take a look at that. I have a comment on that. All right. I would recommend that you label what is turbine A and what is turbine B on that slide. Don't you agree?
Yes,
Yeah.
I agree.
Okay. All right. Now, your presentation seemed to lack some theoretical analysis that would drive some predictions that would be validated by some testing. How do you respond to that?
What kind of?
Well, some kind of algorithm,
Okay, like
formulas,
equations.
theoretical
Okay.
analysis, those kinds of
Well,
equations.
using the apparatus we use, we were using a feeder tube. From that we get pressure change, and then from there we get the velocity. And that's the velocity that we used in the chart that you saw to calculate our or volume flow.
So where are the equations or some of those calculations?
They're on the,
We have to
All right.
post it on.
Do you agree with that?
yes,
Yeah, yeah, we can do that.
definitely.
It will demonstrate to the IAD folks that you've actually done some
No, yeah.
analysis. It's not trial and error or testing and all
Right.
of that. And then it will allow you to make some predictions that you can validate by testing. Does that make sense?
Yeah.
Yes.
All right. Okay, go to the slide on results. Let me take a look at that.
These results are the ones that we did.
This
The
one
first
here,
two.
this one here. Let's see, what was my issue on
I have an issue.
this?
Yeah.
Go ahead, jump in, jump in.
I think you all were in my class, right? You guys see something that I wouldn't like up there?
Significant digits.
Oh, yeah.
Okay,
Anyway, yeah.
The left one's good.
The left one, yeah, so it shows you know how to do it.
Yeah.
So I think that's good. Is that good that that one's okay?
Yeah.
Everybody to walk constantly.
Yeah.
We're for our design.
Those nanowatts built there, right? Yeah, what if that's even less?
you seem to have been reporting a lot of your information in SI units. Some of that you should match it with USA units because the audience that we're gonna have.
Yeah. That's,
You can probably do that in parentheses.
Okay.
Yeah. So nothing drastic, no drastic changes there. Let's see here. Go to the new bearing slide, let me see that, know your, new bearing. All right. You holding that device there, seems like, before air gets to the turbine, there's a lot of friction and interference with airflow with your hand.
Well, actually, in this case, the flow that we're interested in is going through the pipe, so the flow is
Okay,
going,
so-
we're just holding it.
All right, so your hand doesn't impact the flow, but what about the location of that tube relative to the exhaust? How would that impact the accuracy or the predictability of
It
the
didn't,
flow?
well, in these cases, because the rotation was rather slow, it didn't impact it too much. But, you know, we're moving it around to test whether, you know, putting it inside the turbine versus, you know, far away. In this case, it didn't affect it too much.
Or did you draw a conclusion because of the inconsistency of the results from
Yeah,
that?
well, the main reason why we did this in that manner, to do kind of a rough preliminary experiment, was we weren't sure how fast the bearing and turbine would spin. So we actually first wanted to see, without measuring any fixed results, and then later after that, we had everything fixed in position in the right manner. We wanted to see if the bearing itself is actually causing too much friction, because the bearing was not standardly made to be used for this application. It was made for hard shafts that would create a lot of power to move. And so this was a light piece. And so our first idea was, before doing an experiment, we got to first see if this bearing is tall, and it wasn't tall. So when we decided to go with a thinner blade, that actually, by holding it, actually spin real fast, receiving the revolutions that we needed, and we went on to putting a fixed experimental procedure.
We actually fabricated, well not fabricated, 3D printed, a coupler to fit right on there, so there wouldn't be any holding.
Yeah, that's what I mean, so.
Okay, well, that's basically where I was going.
Okay.
So all of your test data then was rigged a little differently, a lot
Yes.
better?
Yeah,
Okay.
yeah, once we determined, hey, this is a problem that's not gonna spin,
Yeah.
then we went with a bigger diameter, and then we fixed the coupler, so there's no human error for touching, it's just.
Very good. All right, that answers my question. Now go to the SolidWorks slide, let me see that. On that note, you may want to make a little sidebar comment about that.
Yeah, putting
Yeah,
this rough as
okay, this one here. Could you do something with the labeling that you got at the top right and bottom left there? As well as the, I guess that's pressure distribution on that top left there?
Yeah, velocity distribution.
Velocity distribution, okay. Well, bold, yeah, I see velocity now, I couldn't see it before.
Oh.
Okay, so make that bolder so it stand out for those of us back here with vision problems. And I think we're all over 40s and 50s, so we're probably all gonna have that problem. I guess bigger. All right, we'll make that 30 and 50s.
Don't say it.
All right, those are all my comments. Good job, thank you very much. You got anything else, Ben?
I stepped in late, so.
All right, well, good. Thank you.
Show us the gist.